Hi, my name is Emil. I'm a production engineer at Shopify, and I work on the performance and capacity planning team. For those of you that don't know, Shopify is an online e-commerce platform. It allows merchants to set up white label shops that allows them to sell their products online. And I have a confession. I really like load balancers. And so today I'm going to be talking about scriptable load balancers and how we use them at Shopify. But before I do that, I'd like to sort of share how I like to think of web services. And so here's a typical, what might be a simplification of a typical web service. Your request comes in through a load balancer. It hits an application server that processes the request. That'll reach out to a data service such as MySQL, and then the information gets passed back, and the response gets served to the user. But we can sort of break this down. The MySQL and the data layer there is, I like to think of it as the data tier. So that's where we have all of the data we need to sort of render the response. Then we have the compute tier. Here is where all the applications code will get executed, and this is where we have typically the business product. And then finally, we have the edge tier. And often, the edge tier is really important because without it, we can't have a highly available service, but it's also almost left without a lot of focus. And if you look at other companies, if you look at companies such as Facebook or Google or some specific platforms like Fastlane, Cloudflare, they put a lot of effort and focus in their edge. And I feel like in the community thus far, we have this sort of dichotomy. You can either be a company focused entirely on the edge, or you can be a big behemoth that has enough resources to go and build out your own load balancer, or you're left with traditional load balancers such as Nginx, HA proxy, that you can have some optimizations in, but they don't provide a lot of value, say, in your architecture. But I think this is a false dichotomy. I actually think there's a third rung in between these two, and that's scriptable load balancers. And so scriptable load balancers is this idea that you take a traditional load balancer and you add in a scripting engine. And that scripting engine will allow you to write scripts, say, in Lua, that'll operate on the request and response flow of a request, and allow you to insert custom logic into your load balancer. And the reason this you would want to use scriptable load balancers over building your own custom load balancer is, at the end of the day, not many organizations have enough people to go and build their own load balancer. We also don't necessarily, there's not that many engineers out there that have the experience of going and building a load balancer from scratch. And once you do go and build your own load balancer, it becomes sort of in-house product that you have to maintain, and you're leaving behind the community and all sort of progress that's going on in the community. You have to then exert work to bring that back in. And as a lot of us probably know, traditional load balancers don't quite cut it. If you've ever tried to do something complex in Nginx configuration, you'll often end up tearing your hair out. And oftentimes, you'll also not even have the functionality you need available in the load balancer. And so some load balancers have tried to counteract this by shipping sort of C plugin or module frameworks. But the problem is that C is inherently unsafe. When you're working with C modules, you have to incorporate lower level details and have context on operations that aren't immediately relevant to the logic you're trying to add or what you're trying to accomplish. And so the scriptable load balancer sort of tool has been slowly growing in popularity, but is still kind of a bit of an underdog, I think. And I'm hoping we can sort of encourage more people to go out and start using them. So these are the three most popular currently scriptable load balancers out there. NginScript is Nginx's proprietary scriptable load balancer, or it's the proprietary language that ships with Nginx. It's a JavaScript-like scripting language. OpenResty is a Lua module that uses Nginx's C module to embed a Lua JIT into Nginx that allows you to write Lua scripts. And then HA proxy has shipped the ability to actually write Lua scripts and also operate on the request. So OpenResty is the scriptable load balancer that we use at Shopify. To give you an idea of what this might look like in your configuration, here's an example of a basic modification/script. That right there is Lua. And what we're doing is we're adding a header that'll set the current timestamp of a response, and it'll return it back to the user. So you can also, in addition to executing the Lua script in line, which grows unwieldy, you can call out to a file that'll load the Lua code and send it back. So why do we want to use scriptable load balancers? Really, it makes difficult problems that SRE teams and infrastructure teams might face, it makes them much easier to solve. So if we think of our edge tier, that's a really powerful location to approach a problem like sharding. So when Shopify was growing, as we had more and more traffic, we eventually outgrew a single MySQL shard, and we had to split it up into multiple shards. And so when a request would come in, we would have every single Rails application, Rails server, connect to all the shards. Then we embedded this logic of deciding which shard a request belongs to into Rails. The Rails server would process this logic and then decide which shard. And since it had all the connections open, we didn't have to do any modification outside of that layer. But as Shopify continued to grow, we outgrew a single data center. And when you have multiple data centers, you end up having this problem of if you try to connect to every single shard across data centers, you're going to be incurring really high latency costs. And so what Shopify ended up doing was we went and we built out a service called Sorting Hat, or a module called Sorting Hat. And Sorting Hat lives in our Nginx's. It's implemented in Lua. And what it'll do is when a request is made to our edge, Nginx will go out and make a request to Zookeeper. Zookeeper will then has the information of where each shard lives. And Sorting Hat is able to deduce from a request what shard that request belongs to. So in this example, a Zookeeper responds saying that the request actually belongs to the first data center. So Nginx will redirect that request back into the first data center. Sorting Hat will run again. And this time, Sorting Hat will say, yep, this request belongs to this shard, so it'll let the request pass through. We'll let the request pass through. So another way to think of the logic that we can add into our load balancers is as service-level middlewares. So quick show of hands, who here works on an application that allows you to embed middlewares in the flow of a request when processing it? Rails, Django, Python, Flask? Yeah, all right. So similar, that's sort of the type of middleware I'm thinking of, but across multiple services. So for example, I've been thinking about how with this move to SRE, we're constantly trying to take away sort of services we would operate to make them sort of self-serve services. So instead of before customly setting up a MySQL server, you would have a service that could bootstrap that whole process on its own, and then an application might reach out to it and boot that up and ask for one. Another example might be an auth service. But what scriptable load balancers allow us to do is they would allow us to actually move that outside service into the load balancer. So then what could happen is when a request comes into the load balancer, the whole auth logic that the application would later have to do and reach out to on its own, say over an RPC layer, that could be handled, and then the request gets passed down to the application, and the application doesn't have to have any context because it can just assume that the request has already been authed. So when we do build out these service-level middlewares, we have to be conscious of the interfaces that we build between the downstream services, or the upstream services within the load balancers themselves. And the reason that's important is because if we don't consciously build these interfaces, we end up having either brittle or stale code that can lead to divergence of logic and could cause service disruptions or incidents. So an example of how we built out an API at Shopify is edge cache. Edge cache is a caching layer we have at the edge that runs out of Nginx. It utilizes Nginx's proxy caching mechanism. Sorry. So it utilizes Nginx's proxy caching mechanism, and it augments the functionality. Nginx's proxy cache is really good at HTTP caching, but caching static assets, not dynamic assets. So what edge cache will do is edge cache will allow us to skip entirely talking to our backend Rails servers. So a request will come in, it'll build its cache key, request that from the cache, and then Nginx will serve it directly. And so here, this is an example of a response we might have from a Rails server. The important part to notice is the vary and the cache control headers. So HTTP caching, the HTTP caching RFC allows for cache control extensions. So that would be this cookies argument at the bottom in the cache control header. So what this caching extensions allows us to do, or what custom extensions allow us to do, is we can add in our own arguments, have our own logic, and any upstream or downstream caching server will ignore it if it doesn't understand it. So what edge cache does is it goes and reads the cookies argument, and it'll use that to pick specific cookie values out of the cookie header. So why is that important? The vary header, which is HTTP's mechanism for building cache keys, only allows us to use entire headers. So if you were to put in the cookie header, you'd end up splitting your cache key based on every single possible value across all cookies. So you have a fully fragmented, your cache becomes crazily fragmented. So when we can split this out, we can actually tell our Nginxes can build this cache key that only will look into a specific, say, session ID. But then the problem is that upstream cache servers don't, well, they'll just ignore it. But what we can do is we can strip it entirely so it looks as if we've never sent that before. And so this would be the final response that a client would get with edge cache. So when you end up implementing and adding custom logic into your edge, what quickly becomes apparent is it's difficult to accomplish high-value things without accessing or creating state. The edge does allow us to operate across a full request. So you do have the context of a single request. But having that bigger picture is very valuable and will quickly become apparent how valuable it is. So you can actually break down the way you think about the state from a load balancer. So the first one, or sort of the smallest scope, would be the host state. This is Nginx or the load balancer only tracking state and only tracking what happens on the request going through that load balancer. And the important part is that with each sort of rung of state, the resiliency and complexity potentially increases. So with a host, if you are only looking at state that touches a host, we have no need to have any cross-communication between machines. If we lose it, no other machines are impacted, which is important because we want to be thinking about our load balancers. We want to ensure that we don't add any additional or too much additional complexity that substantially lowers the availability of our load balancers or our edge tier. So beyond the host state, we have the DC state. In the DC state, you have sort of a couple options. You can either have cross-communication between hosts, or you can have a communication between hosts to a single data store. Again, both of these have their own complexities, and they also have different guarantees. If you want a data store that's highly available, you may have to compromise on the consistency guarantees you can get from your host, or you can get from it. And then sort of the final rung in the scopes of state is global state, and this is state across all data centers and across all load balancers. And here you might have, say, a service like Zookeeper, but this rung of state is also the most complex one. This one will often require you either to substantially compromise of consistency or substantially compromise on latency. So as you're sort of going through and you're building out these modules, you end up coming to you run into a way where you can actually, if you shift slightly the way we will typically approach a problem, we can, if we slightly shift the way we approach a problem, we can actually utilize a lower rung and scope of state to accomplish the same, to solve the same problem, accomplish the same desired goal. So one thing is that you would, ideally, and what we found to be very valuable, is using ECMP at our edge. This means that we can have a very high likelihood that any behavior in the types of requests we're seeing on a single load balancer will likely happen in all the other load balancers. So an example of when this is valuable is when building a throttle. So with a throttle, the almost default solution would be to have sort of a global DC state or a global state across all DCs, and have a data store that's keeping the count of requests across all load balancers. And then when one load balancer goes over, you would have that load balancer check with the global data store and then kill the request if it's over the limit. So again, you're having each load balancer on every single request talk to a single data store in line with the request before it allows the request to go to the upstream application. Instead, with ECMP, we can likely expect that every load balancer will see an equal number of requests. So we can actually split our throttle rates by the number of load balancers we have. So when a request hits a load balancer, only each load balancer has to locally increment that count. Then, if a single load balancer goes over the limit, the only data store it has to check is the local one. So this has its benefits and drawbacks. One of the benefits is, like I mentioned earlier, the latency benefits, or performance and availability, but you could also get some jitter. So you have to sort of start shifting the way you might think, where instead of having exact values, you might have to lower your throttles or bump your throttles to get where you want to be. So some lessons we learned at Shopify from building scriptable load balancers. So the first is deterministic configs. When Shopify shipped its initial version of its scriptable load balancers, we had all our configuration for Nginx and cookbooks, and we had the application code, because clearly we're writing some application, in a separate repo. But setting that up and merging those two was still something handled entirely by our cookbooks. What ends up happening is, over time, instead of fully treating this service or this layer like an application, we're still treating it like a smart piece of infrastructure. And what would happen is the application code would make some changes, but the cookbook changes wouldn't match that, or the opposite would happen. So one lesson that we're working to rectify now, and that will very likely bite you if you don't from the get-go have this in mind, is ensuring that all configurations are deterministic and that they're merged and embedded with the application code that you're adding to your load balancers. The other is testing. So at Shopify, we ended up writing our own integration test suite. If you've ever written Rails code or used something like Minitest, this will look very familiar to you. And that's the goal. Currently, development on scriptable load balancers and the development tooling around it is very rough. And so rather than having to open up curl every single time, having a test suite that you can run and that's quite readable has been immensely valuable. The other thing that we've had to learn the hard way is how we do deploys. The edge tier is almost like a funnel where it has typically the least number of nodes, but handles the most amount of traffic per node. So if you make a mistake on any of these nodes or you deploy bad code, you end up hitting a substantial portion of your traffic. So figuring out how to do canaries, how to properly stage your code is something that doesn't have an immediately easy answer, but it's something that requires thought and concentrated effort to get right. And the final point is community. We've had to learn that the community, while active, is still quite small. So what you'll often find when you'll go out and do some research on OpenResty or any of the other scriptable load balancer options is that there'll be great like hello world guides, but you won't have the getting to the next step. You won't have how do I put this application in production. You will find, though, how to optimize my code to the nth degree, but that middle point is very important to help more companies start integrating this, and it's something we've had definitely seen some trouble. So that's the end of my talk. Like I said, there's quite a lot of potential, I think, and power that we can all gain from using scriptable load balancers. And I think the tide is turning. I think as more and more companies are beginning to use these tools, the community or the documentation is improving, and it's fostering sort of additional tools that will be plug and play and allow us to approach scaling or difficult problems, or what we once thought difficult, in much simpler ways. Thanks.